Hi everyone. So this lesson, lesson 2.3, is going to talk about integration by parts. So far in the first two lessons, you've seen rules for integrals that are integrals for certain situations. Okay, so we had the power rule. Okay, we talked about logarithmic exponential functions. And then we talked about a bunch of different instances of trigonometric functions. All of those were the corresponding integration rule for a certain derivative. Okay, so for example, the derivative of sine x is simply cosine of x, right? So the corresponding integral rule was that the integral of cosine x dx is simply sine x. Okay, so it's rules like that. This lesson is no different. Integration by parts is actually the integration rule, okay, that reverses essentially the product rule. So remember with the product rule, we had two functions multiplied together. Let's say we have x times sine of x. And so when we had them multiply together and use the product rule, we let one function be u, let's call it x, and one function be v, which would be sine x. And then we found the corresponding derivatives. So du by dx is simply 1, and dv by dx, in this case, is cosine of x. The product rule, when two functions were multiplied together, stated that that derivative was equal to the function that you named u times dv by dx, or the derivative of the function v, plus the function v that we labeled times the derivative of the function u. Okay, so if we work that backwards with integration by parts, what we have is if we take the integral of this function here, okay, the integral of a derivative is simply going to be whatever is inside the brackets. So we're left with u times v. And that has to equal the integral of this first piece here, which is u times dv, minus the integral of the second function here, which is v times du. Sorry, that should say plus. Okay. So that's just simply using basic integration rules. Now, when we're finding an integral, oftentimes we actually are given something like the integral of x sine of x. So the way we have it currently written here isn't going to serve our needs because it has the multiplication of two functions u and v on one side of the equation. So we want to have just an integral on that side of the equation. Okay? So in order to do that, we have to simply move one of these integrals. In this case, we'll move v times du to the other side of the equation. And if we do that, we end up with the integral of u times dv, that's what's left on that one side, is equal to the function u times the function v minus the integral of the function v times du. Okay, so we're following the same method where we're starting, except we're starting with an integral. But in this case, we're going to start with an integral. Again, I'll go back to x sine of x dx. And by starting with the integral, we have to set one function to be u. Okay, so in this case, I can pick x. And the other function, instead of setting it to v, remember when we did the product rule, we set it to v, it's going to be set to the other piece that's sitting here in the integral, which is dv. So in this case, dv is sine x dx. In other words, the integral, or the derivative of the function v. Okay, so it's different than the product rule in that sense. So if you look back up here, what we have left to find is now we know what u is, we don't know what v is, and we don't know what du is, or the derivative of the function u. So if we solve for those, du by dx is simply 1, or you can write it as du is equal to 1 times dx. All I did was I took the dx and I moved it to the other side. Okay. For dv, you then have to find the integral. Okay, so the function v must be the integral of sine x dx. And you can see that this is one of those functions that we looked at in the last lesson where we had tables of values. So those tables of trigonometric integrals, all of those I will provide to you on a test. So I highly recommend you have those with you as reference when you're doing these problems. So the integral of sine x dx, if you look at that table of values, is equal to the negative cosine of x. Okay? For integration by parts, we don't have to add the constant until the very end when we're done. And that's because I won't show you this in the example, but going back to this original equation, mathematically, the constant will actually always cancel out between it being substituted in here and it'll end up somewhere here, okay? And that's because of this minus sign here. So I won't show you that, but just know at the very end, you then can add a constant. So let's look at our first example, okay? The integral of x times cosine x dx, okay? Remember the formula for integration by parts. The integral of u dv is equal to u times v minus the integral of v times du. Okay, so we have to set something in this function to u and something to dv. So I'm going to again just go from left to right here. I'm going to let u equal x and dv equal to the remaining term, cosine of x dx. So what I need now is I need du. So if I take the derivative, du by dx is simply 1. So if I want to solve for just du, du is equal to 1 times dx, or just dx. Okay? To solve for v, I have to take the integral of this function. So v is therefore the integral of cosine of x dx. Remember from our last lesson, the integral of cosine of x is just sine of x, right? Okay. We don't have to add the constant in this scenario here because it will always cancel out between these two functions here, okay, with it being subtracted. So we don't have to show the constant. At the very end of this integral, we'll have a constant at the end of the function, but we don't have to do it during these intermediate steps. So now we have all the pieces, u, v, and du. So we can simply substitute those in. So the integral of u dv is equal to u times v, which is x, times v, which is sine x, minus the integral of the function v, sine x, times du, which is simply dx. Okay? So now we just have one more integral to do, and it's the integral of sine x dx. And we know that we still have x sine of x minus, we know the integral of sine x is negative cosine of x. Okay? So we're left with x sine of x, and we have two negatives here, so that becomes plus cosine of x. And at the end, we will add our constant. Okay? So seeing with integration by parts, we're breaking it down into easier, more manageable pieces that we know the basic rules of for integrals and derivatives. Okay? So our final answer is simply x sine of x plus cosine x plus our constant. Okay? Okay, so let's look at a second example. Evaluate the integral of 6x e to the 2x dx. So you'll start to see that integration by parts is a very powerful tool to find a lot of different integrals. So it doesn't just have to be trigonometric functions or functions that have just x. Okay, in this case we had a function of x and a trigonometric function in the first example. In this case now we are bringing in an exponential function. So the formula remains and is used the same for all of them. The integral of u times dv is equal to the function u times the function v minus the integral of v times du. Okay? So we have to set one of these functions as u and one as dv. So I'm going to pick u is equal to the 6x. I usually go from left to right. I can't say for sure that that is the best method. It hasn't really steered me wrong in all the time I've been doing calculus, but it's totally up to you in terms of which one you want to pick. One will usually yield easier integrals and slightly easier derivatives, okay? So I'm going to pick u as 6x, and the dv function being the remaining piece, e to the 2x dx. So now I need du. Okay, so du by dx is just simply 6. Or du is actually 6 dx. Okay, I do that kind of as a formality, to have the dx function because I want it to kind of end up in this final integral here. So now we know what dv is, and we know what the integral is for an exponential function. So we know if it's a function e, the integral of e to the u du, in this case, is going to be e to the u, normally plus a constant. We don't have the constant here. The piece that this doesn't note is that if you have some kind of constant value here, it's normally going to be 1 over whatever that constant is. Okay? So if I do that, I know that the integral, or v, is going to be equal to the integral of e to the 2x dx. And in this case, I do have a constant of 2 here. Okay? So when you take the derivative of e to the 2x, you're going to have e to the 2x multiplied by the derivative of this exponent, which is 2. So we have to make sure we remove that. And we remove that similar to the power rule by putting 1 divided by that number. So we have 1 over 2 e to the 2x. Okay? And again, I don't place a constant here because I know it will cancel out in this formula. So now we have everything we need. We can just substitute it in to our equation. So the integral of u times dv is equal to the function u, 6x, times the function v, 1/2 e to the 2x, minus the integral of the function v, 1/2 e to the 2x, times du, okay, which is 6 dx. So you're going to see a couple items that I can simplify here. First is I have a 6 in the numerator and a 2 in the denominator, okay, in this first function. So that just becomes 3x e to the 2x. Secondly, in this integral, remember, anytime you have a constant in the integral, you can move it out of the integral. So again, we have a 6 in the numerator and a 2 in the denominator. So that just becomes 3. So we end up with minus 3 times the integral of e to the 2x dx. So we've already done this integral, right? We did it right here. And you'll see that happen a lot because with the e function, remember the derivative always keeps that e function in there, right? So you're going to see that as a common theme with these. So our next step now is we have 3x e to the 2x minus 3. Remember, the integral of this is exactly the same as what we've already done, 1/2 e to the 2x. Okay? And then obviously at the end, now we're at the very end of the problem, we can add a constant. So if I wanted to simplify this one step further, I'm just going to do 3x e to the 2x, and I'm going to write the second term as one fraction. So 3 times 1/2, we have minus 3 over 2 e to the 2x, and then plus a constant. Okay, so you can see that integration by parts really helps you to do what would otherwise look like a more complicated integral rather quickly by piecing together multiple easier integrals and parts and then placing them together. So the next example I want to show you, this is our third of 4 examples I'm going to do in this lesson, is what if we have to perform integration by parts twice? So looking at the formula for integration by parts, we have the integral of u dv is equal to u times v minus the integral of v times du. Well, what if we can't take this integral and we have to do integration by parts on it? So that case does arise. Okay, so it's a couple additional steps when we're looking at it. So let's look at this integral. It's the integral of x squared sine x. Okay, so I'm going to let u be x squared, and dv in this case be sine x dx. Okay, so always from left to right. It's just always the way I've done it. So du is simply 2x, and then multiplied by dx. And v now is the integral of sine x dx, which in this case is negative cosine of x. Okay? So if I substitute those in, I get the integral of u times dv is equal to u, which is x squared, times v, negative cosine of x, minus the integral of v, which is negative cosine of x, and du, which is 2x dx. So you can see I'm going to simplify this first. So I have the integral of u dv is equal to negative x squared cosine of x. And then we have two negatives here and a 2. So I'm going to move the constant outside of the integral. So plus 2 times the integral of x cosine of x dx. So we're back into the same problem here, right? We have x cosine of x, and we can't do the integral. Okay, so in our first example in this class, or in this lesson, we had to do integration by parts on that. So that means you have to do integration by parts a second time. Okay? So I'm going to use the same notation, right? I'll just separate it like this, and I'll do it in a different color. So again, we're doing it just on this x cosine x dx. Okay? So we'll let u be x, and we'll have dv equal to cosine of x dx. So now du is simply the derivative, which is 1 times dx. And v now is the integral of cosine of x dx, which in this case is sine of x. Okay, so having all of this, now we have to substitute that into the equation. So I'll keep the equation as the one color red, and then when we get to this integration by parts, I'll switch back again to the purple color. So substituting in, we have the integral of u dv is equal to negative x squared cosine of x plus 2 times, okay? Now filling in this information, we have u times v, which is x sine of x, minus the integral of v, which is sine x, times du, which is in this case just dx. Okay? So doing this integral, okay, I'll do it on the side. We know that the integral of sine x dx is negative cosine of x. Okay? So substituting this in, we get the integral of u dv is equal to negative x squared cosine of x plus 2x sine of x. Okay, so that's this term here, multiplied by the 2. Minus, again, multiplying the 2 in, 2 times this integral, which is negative cosine of x. Okay, then at the end of this, again, we add the constant. Okay, so if I want to keep with what I did in the previous, this cosine of x would be in brackets here, okay, in purple. So simplifying this, just collecting all the negatives and everything else, we get that it's equal to negative x squared cosine of x plus 2x sine of x plus 2 cosine of x plus a constant. So you can see that by doing integration by parts, we added another term into this integral. So you can see that now we have 4 terms if you include the constant. But the way you do it is still exactly the same. Okay, so it doesn't change when you have to do it for a second time. It's just a couple of additional steps. Okay. So our last example, okay, we're going to look at, again, another type of function. We've done trigonometric functions, exponential functions. Now we're going to look at ln. So the integral of ln of 2x dx. Okay, so we don't have an integral for that. We have that the integral of 1 over x dx is the ln of the absolute value of x. Okay, we know that integral from our second lesson. But we don't have an integral of ln. So again, we have to use integration by parts. So when we do that, we have, again, starting with the formula, the integral of u dv equals u times v minus the integral of v times du. So in this case, I'm going to let u be equal to the function ln of 2x. And in this case, dv is just going to be what's left over, which is just dx. Okay, that's the only piece that's left over. Again, you take all of the pieces from inside this integral sign. So we can solve for du by dx. Remember, for ln, it's 1 divided by whatever is in the brackets here, 2x, times the derivative of what's in the bracket. So the derivative of 2x is 2. So du by dx would then be, we have 2 divided by 2x, or just 1 over x. Okay, meaning that du is 1 over x dx. Okay, so that's just moving this dx to the other side of the equation. So v then is just the integral of dx. Okay, and remember the integral of dx is simply x. Okay, so with all these pieces of the puzzle, we can now substitute them in, and we get the integral of u dv is equal to u times v, which is x times ln 2x, minus the integral of v, which is x, times du, which is 1 over x dx. So you can see here the x's will cancel, and it just becomes 1. So our integral becomes x ln of 2x minus the integral of just dx. Again, one that we've already done here. Okay? So knowing that, we can then simply substitute it in. So we have x ln of 2x minus, this is just x. And then again, at the very end, we add a constant c. Okay? So you can see that this method really makes these integrals that look more difficult a lot simpler to follow if you just follow these steps in order. Okay? So this was a shorter lesson. Integration by parts is one that definitely takes practice. I do encourage you to look at these practice problems. If you do have any questions, send me an email or feel free to ask them in the tutorial. Thanks, everybody.